We can gain a lot of knowledge about the interaction between different molecules if we look at what happens to the state variables when we mix two things together. The process of mixing is shown here. I take three different pure substances and make a mixture of those three substances. So my final state is a mixture, and my initial state are the pure substances. If I want to calculate the change in some variable for this mixing process, I must determine the value of that variable in the final state and subtract that from the value in the initial state. The initial state is simply the pure substances, and so I simply need to take the number of moles I'm going to mix times the value of the variable for the pure substance per mole and add all of those together to get the value of the variable in my initial pure states. In the mixture, it's a little bit more complicated, as we saw with chemical potential, because there can be interactions between different types of molecules, and we have to divide those interactions up into a term that describes the contribution of a single component to that variable in the mixture. And so I use the partial molar quantities to do that. Just as the partial molar Gibbs free energy is the chemical potential, I can look at the partial molar entropy and the partial molar enthalpy and the partial molar volume in order to figure out how much each component contributes to that particular variable. I can rearrange this equation by getting all the terms for component 1 together and all the terms for component 2 together and all the terms so forth and so on for component C together. So the change in a given thermodynamic variable when I mix is just the sum of the difference between the amount that component contributes to the mixture minus the amount in the pure substance. As we know, the partial molar Gibbs free energy is simply the chemical potential. Because the entropy is the opposite of the derivative of the Gibbs free energy with respect to temperature, we can show that the partial molar entropy is equal to the opposite of the derivative of the chemical potential with respect to temperature. For the enthalpy, we know that the enthalpy is equal to the derivative of the Gibbs free energy divided by temperature with respect to temperature times minus T squared, and so the partial molar enthalpy is equal to minus the temperature squared times the partial derivative of the chemical potential divided by temperature with respect to temperature. Recall that the chemical potential in solution is equal to the chemical potential of the pure substance plus a correction for the substance not being pure, where gamma is the activity coefficient of the substance I, x is the mole fraction of substance I in the solution, and gamma times x is equal to the activity of that substance in that solution. Using this definition of the chemical potential of each component in the mixture, and our definitions for the partial molar quantities, we can plug into our equation for the change in a property and show that the delta H of mixing is given by this equation, delta S of mixing is given by this equation, and delta H of mixing is given by this equation. If we look at delta G of mixing, we can see that depending on whether the activity is greater than 1 or less than 1 for the components, delta G of mixing will be greater than 0 or less than 0. The natural log of a number greater than 1 is greater than 0, and the natural log of a number less than 1 is less than 0. Remember that delta G being less than 0 indicates a spontaneous process. And so only when the activities are less than 1 will the mixing be spontaneous. So for instance, ethanol and water mix spontaneously, but oil and water do not mix spontaneously.